Dzień dobry Państwu. Ja wprowadzę naszego gościa, który wygłosi swój wykład po angielsku i dlatego, żeby się dostosować, to ja też przełączę się na angielski i powiem dwa słowa. Piotr Łuczak is a graduate of the Silesian University of Technology with nearly 20 years of experience in embedded control development, simulation, and XIL architectures for domain control systems. He has spoken at international events, including conferences of the Digital Twin Consortium in the USA, with a focus on digital twin life cycle and applications. Currently, he serves as a Chief Applications Officer at Tritem P.S.A. Piotr, please start.
All right. Hello, everybody. First of all, thank you for having me, for inviting me to this presentation. I'm going to share my screen. All right, is everything visible?
Yes.
So, all right. Perfect. So again, today I'll be talking about applications of digital twins in safety critical systems across industries. This is a seminar that I was giving also at the Digital Twin Consortium the other day. Slightly extended since then, but it comes directly from the conference. So let me start with the agenda for today. There's going to be a brief introduction. Then I would like to cover the definitions a little bit. Then talk about how we are building the digital twin here at Tritem. Talk about a case study, which would be a real-life example of such a twin and its use in the real world. And then there will be some space for Q&A at the end of my presentation. So let's dive right ahead into the introduction. So myself, I'm currently a Chief Applications Officer at Tritem, or Tritem, depending on how to pronounce this. And I've been with the company for 16 years already, so long enough to see the technology I'll be talking about today grow, getting mature, and also seeing our customers benefiting from it and coming back for more. The company itself was established in 2004, so slightly over 20 years ago. We're based in Poland. Also, there's one location in Warsaw, in Germany, and in the US. So the main engineering office is in Katowice, in Poland. We're partnering NI and Emerson for over 15 years, using their tools and solutions. And we have a fairly sustainable customer base across Europe currently. The company is not very big. It's around about 65 engineers right now. We have our own multi-purpose workshop where we can build prototypes, build hardware, and also a landing zone, which is a place for our customers to store their equipment, store their hardware, and use it remotely. And as a company, we're specializing in delivering digital twins as simulation, test, and validation systems for safety critical systems. So that's the essence of what we are doing. And because I'll be talking a lot about simulation and digital twin today, I thought it would be a good idea to start with some definitions so that we know exactly what we're talking about. Both of these terms are, to some extent, umbrella terms, let's say. So when people hear simulation, there could be several different understandings of what it is. In our case, simulation is a model which is mimicking the operation of an existing or proposed system. and helps providing evidence for decision making by testing different scenarios of process changes. And the digital twin, by comparison, is integrated virtual representation of a real-world entity and process. So obviously, the definition of digital twin, which you can see here, is taken directly out of the Digital Twin Consortium glossary, and I think it describes very well what it is. The important part is that the digital twin always comes with a specified frequency and fidelity in its operation. So there could be digital twins which are reflecting the real world device in tiniest details. There could be ones which are a little bit more abstract, but still serve a similar purpose. Now, let me start by explaining how do we actually came to having a digital twin. What is the real cause? What's the real aim here? And basically, when we're talking about safety relevant systems, it goes without saying that those systems must be rigorously tested before the product is deployed to operation. That's obvious, or in this case, that would be before it's launched into space. And because of that, because of the fact that we need to do a lot of testing, we take a look at the amount of time and effort it is required for cleaning the test or cleaning the bugs that are discovered, or fixing the bugs from the time they were discovered to the time they are fixed. So when we find an issue in the control software at the very early stage in the development phase, then obviously it's very quick to fix it. So typically even the developer would be able to fix it themselves. Then another stage would be laboratory testing. So whenever we find a bug in the lab, it takes a little bit more time to fix it. It takes a little bit more time to replay it to see if the fix is done properly. But if we find it on a prototype, it is likely going to take even more time to fix it, to get rid of. And the last option here is when we find a problem already in the operation of the product. So in this case, when it's already operating in the orbit, then the effort and the time required to fix the problem is basically growing exponentially, and in some cases might be even just impossible to do. So there are several downsides of it, not only the cost, not only the time, but also in case of commercial products, releasing a buggy software to the public is also causing the let's say a blow to the image of the company that released it, principally. So our aim here in the whole story was to shift the bug discovery process to the left as much as possible. So the more problems we can discover at the early stage, the more problems we can fix at the early stage, the more time we save, the more the safer the product is in the end. So so that's the general goal here. And so our first step to having a digital twin is starting with the electronic control unit. So we're looking at the electronic control system. It could be any kind of control system, in fact, but typically we're focusing in this technique on systems which are controlling other subsystems. And typically there would be a electronic control unit, which is just a piece of hardware, a processor, let's say, in a very abstract way, running some kind of code. And so we start with creating what is called a hardware-in-the-loop solution for testing this kind of device. So the whole project starts at the beginning, and typically the controller is already selected or is there. Developers start developing the code. The code is already there, and we start thinking about testing the code that got created as early as possible to shift this whole failure detection to the left as much as possible. And so one way to do it, and the way that we are doing this, is to create a simulated environment around this control unit, because typically at the early stage of the project there are various constraints. Let's put it like this. So the subsystems are missing, or there is the wiring diagrams which are incomplete at this stage. The product is not yet constructed fully, so the only way of starting the tests really, really early with the real control unit is to surround this control unit with a simulation. And the simulation is going to make the controller think that it's operating in the actual product. Obviously, the simulation needs to be connected to this piece of hardware. So there are some interfaces that could be buses, like industrial standards buses, like CAN, like TCP/IP networking, like even SpaceWire, or some other kind of industry standards that we can attach here. Also, we're mocking the digital and analog IOs that are related to this ECU here, so that all the inputs and outputs of the control unit are simulated, and the operation of the software on this piece of hardware doesn't differ in any way from the operation in the real device. And let's talk a little bit about the simulation part here, because the simulation in this setup is typically related to a lot of constraints and limitations. So we have things like a tight schedule on the project itself. So again, if we want to make it very, very early at the very early stage of the project, then we cannot afford spending too much time on preparing those simulations. And we cannot spend like months on implementing them, because that wouldn't make really sense. Wouldn't really make sense in this case. Obviously, there are some budget constraints. So the more time we spend on developing the simulation, the more costly it gets. So this is also a factor that we need to take into account. Also, the time resolution of the simulation environment that we're building needs to be adjusted to match the interfaces of the system, so that we never get into a situation where our simulation is producing some simulated inputs or outputs for controller, and the controller is already one step further, because that also wouldn't reflect the way it operates. And finally, performance also needs to be taken into account, meaning that it's best if the simulation can just run on a regular piece of hardware instead of having to invest heavily in hardware and computing power. So our answer to these limitations and constraints is selecting the appropriate level of fidelity for simulation. And so generally in our daily work, we encounter different fidelity levels on different levels of the project. Let's put it this way. So there would be system design level simulations that are pretty abstract and very general. And in the industries we're working in, typically on the system design level, those simulations would be presented to the stakeholders to make sure that the product that is designed is designed properly. but at a very abstract level. So this is not very usable for our case for control software testing. Then on the other side, on the other end of the spectrum, we have physical simulations that would be fluid dynamics, that would be mechanical simulations of materials, of tensions, physics, and things like that, which are very, very accurate, but at the same time, pretty demanding in terms of time, in terms of the effort that is required to build them, and also they are rarely optimized enough to be able to run in real time, so that they couldn't really be directly connected to a piece of real hardware, because the calculation time of this simulation is so, this kind of simulations is typically very, very demanding and high. So our solution, what we propose and what we're doing and implementing in our digital twins is something we call a behavioral simulation, which is nothing else than just logical models. So these simulations reflect the way that that the system around the controller behaves, and they are, let me put it this way, as precise as required, but not more precise. So we make sure that the controller, from its perspective, is really seeing the behavior of the system as it would see it in the real device. And but at the same time, we cannot let ourselves spend indefinite amount of time on implementing every single detail of how those external components actually behave. And we divide these behavioral simulations into two modes. One is the behavioral simulation running on a standard machine, and this can go down to the cycle of 1 millisecond. So in many cases, in many industries, that's totally sufficient for controller testing. When bus telegram communication cycle is let's say at 8 or 4 milliseconds lowest, then it's enough to go down to milliseconds with the simulation to be able to actually mimic the behavior of the system. But there's also another option, which is real time, and this is when we want to connect more than one piece of hardware to the controller, and then we have to make sure that that these the timing requirements, which are done in microseconds, are also met. So this is what our behavioral simulation engine is also capable of. And now, so having this simulation connected to the electronic control unit, as I already mentioned, we have a setup which is called the hardware in the loop. And typically it looks like this. So this is just a rack case with the real controllers, with some kind of an industrial PC, some IOs, buses, and gateways. And so this is again what we call the hardware in the loop mode. And then another option is when this hardware availability is also creating issues in the project. Let's say there are very long lead times, or there are difficulties to get as many setups of the hardware as are required for the project. So if there are many people working on the project simultaneously, then obviously the availability of hardware can become a real bottleneck. So in that case, we can switch to the system to the mode of an emulated control unit. So in this one, we are moving the entire source code to a software domain. We have an emulated system which is running the same software as the controller would, together with the simulation, and it all can be logged into a single PC. What's also very important in this mode is the fact that because we have a full control over the execution of the code, we can introduce things like time slicing, or just controlling the time, slowing down the time of execution, looking into the code, looking into the memory of the emulated control unit, which makes it possible to debug even the most complex and demanding cases. So this is software in the loop, and the abbreviation is SIL. Then we've covered the hardware in the loop, which is HIL. There's yet another mode in our systems, which is called MIL, when we're looking not at the control software that we're testing, but rather at the model of the control software. It's something that would be written in a Simulink model or something alike. So we can also hook it up to the loop and run all these tests on the model even before the actual software development starts. And all these three together, they can be described and are often referred to as a SIL or XIL, which stands for X in the loop principle. So just anything in the loop, and this refers to a generalized framework for dynamic testing, which again uses just various virtual test environments at different abstraction levels. So whether it's with a piece of hardware, there's hardware in the loop. With a model, there's model in the loop. With software only, with emulated control software, there we have software in the loops. And this SIL that we are building, is playing different roles depending on the stage of the product development. So this diagram here shows a timeline of the product development. We start with development and test phase, where the SIL is fulfilling the role of a classical virtual testing system. Then it goes to commissioning, so making or assembling the final product, and then testing it yet again with the use of the simulated models. But when the project is launched, either into operation, production, or in that case into space, what we've got here is nothing else than just a full-featured digital twin of the product that is operating. So that's how the SIL system that we're building becomes a digital twin once the product that we've been working on is brought into operation. And within the Digital Twin Consortium, this is often referred to as a pre-twin. In this naming convention, the SIL would be the pre-twin in our case, and the full-featured digital twin is what comes out of it when the object is being, or our product is being brought into operation. And so we end up having this digital twin, and here are some use cases that this is being used for, and it's currently actually used for also by our customers, but I'll get to this in the case study later on. But there are several use cases. One of them is certification and recertification, meaning that we can, after the product is commissioned, we can use the digital twin to introduce some changes and then recertify it basing on all these tests that we could run on it. It could be also set up in such a way that the outputs of those tests, typically automated tests, are producing input which is, or data which is considered input for device homologation. So that's particularly important in the rail industry, where we are most present currently. What else? If the project or if the product that we are building is operated by a human, then the digital twin can be easily used to drive training rigs, so that we can take the twin and sit the operator in front of it, and we have a guarantee that it's going to behave exactly like the real thing. We can play all the scenarios, all the even the ones that are let's say safety relevant, so some emergency behavior of the system. We can simulate or imitate the failures within the system as well. Another use case would be diagnostic capability. So in case the real object that is operating in the field or in space is sending us some data, we can feed the data to the digital twin and see how it's behaving. In case there's some problem with the behavior, we can go deep into the software which is there, and or hardware design as well, and figure out what's the root cause, if that's the main controller, if that's the one of the subsystem controllers, or something else. And finally, obviously, also upgrades. So whenever there's a need to upgrade either hardware-wise or software-wise the device that we are talking about, we can do it first on the digital twin, alter it, see if it still works the way it is expected to, and then perform the upgrade when we are 100% sure that it's not going to break anything and it's actually improving things. And so I'd like to talk a little bit more about this particular use case. There's a very nice story related to this use case, right from the Bright mission example in the space industry. So in that mission, those satellites were equipped with 3 or even 4 identical board computers for redundancy. Those computers were assigned different options at the beginning. So, but they still maintain the same level of access to the sensors and actuators, like the energy management, like DCS or things like that. And in this particular one, those satellites were built by 3 different countries. I believe it was Canada, Austria, and Poland. And Austria has deployed their satellites first. And as they were already in space, it turned out that because of some sort of radiation coming from the SAA, the South Atlantic anomaly, one of those processors got damaged, and as a result, the team on the ground had to construct or not construct, but reprogram the whole device to alter the original functionalities of those processors, so that the ones that were still operating correctly could take over functionalities of the one that got broken. And it ended up with a success. This is a very, very good use case example for why one would need a digital twin on the ground. And I'd like to go to the case study, but before we do this, just one introduction that I need to make. This is one of the key components of our digital twins. This is called ELMO. It is a simulation engine, or actually electromechanical simulation engine, which is capable of consuming project documentation and data as inputs, and producing a fully working simulated object as an output. So it reads technical drawings and schematics of the system. It orchestrates the execution. It allows us to alter the state of each and every individual component of the system. So we can simulate a problem, let's say with a relay or with a switch or a broken wire, and see how the system responds, how the system behaves in case of a failure. And it's obviously crafted to meet all demands of automated testing systems. Again, these systems typically come with a full automation suite. And right now we're thinking about working on employing ELMO for failure analysis, MEA, and worst case analysis together with CBK to introduce some kind of automation into this otherwise long and tedious process. So again, ELMO is the foundation, and let me go straight to the use case. The use case will be from the rail industry. This is where let's say, our strongest field of operation right now. And I'll be talking about a project which is called Siemens ICX. This is the fourth generation of Siemens high-speed trains, for which we have created such a digital twin, what I've just described. So starting with the cell, starting with the hardware in the loop, and connecting it all together up until the point where we had the entire train, entire object in this case, reflected in its digital or semi-digital, because in this case there were also some physical elements like cabling. We had it all in place, and it was a pretty large one. So the train like this, you can imagine, consists of 12 cars, each and every car represented by one hardware in the loop setup. Then all these hardware in the loop setups were interconnected with the wiring that was actually reflecting the real length of wiring in the real thing, meaning that all the delays that were occurring on the transfer layers could be detected, could be handled in this testing setup. And these racks were also equipped with Elbow, the engine that I just described. They were powered by NI-PXI hardware as well. So we use a lot of cards from National Instruments for different interfaces, like EtherCAT in this case, CAN. And Elmo is also running on Veristand. Veristand is a platform from NI for this kind of applications. So the whole system is backed by a serious company with a serious record of reliable and precise hardware development. And so we delivered this at the development stage. This was a project that was reported to have saved Siemens a couple of $1 million in the end, because we were able to identify a lot of issues still, let's say, on the ground, or still before it was commissioned to operation. And part of them, if they went unnoticed, then they would have probably caused a lot of damage physically, and also a lot of delays, which would then result in contractual penalties for Siemens. So it was a very, very successful thing in the end. And then once the train got commissioned, it got switched to the digital twin mode. So again, referring to this conversion from the XIL to the digital twin. And the whole thing is currently operating, even though the project started, I think, in 2016. The whole digital twin is currently operating at Siemens premises, and they are still using it. They're using it for all these purposes that I mentioned before. They've been training people using that. They've been diagnosing problems. They've been doing upgrades to their design because of some requirements, and it's still up and running and doing a good job out of that. Now, one of the challenges of this design, again, here we had 12 separate systems, in fact, which were connected together, was to have this simulation, this behavioral simulation, the representation of the, subcomponents of the train synchronized in time. Here we're talking about some fast simulations like pulse braking, like some actions on the train with the propulsion system, which require really fast communication between these racks. And in order to be able to debug this efficiently, we had to come up with a mechanism to synchronize all of this communication to under 1 millisecond level. And so just to illustrate some challenges that this kind of design poses, we had to implement something called a PTP, which is the protocol, precision time protocol, that's the abbreviation, and specified by a EEE. And it ensures that when we're getting the information out of the system, getting the logs, looking at the details of what is going on inside of the system, we can actually be 100% sure about the order of occurrence of all of these events across the entire thing. So this is, this is one of the most challenging things about that, and still operates to this day. So just to wrap up what I've been talking about, this digital twin approach that we are working with on a daily basis, and we're trying to actually expand to many other industries that have all these things in common, meaning that there is a multi-layered embedded control system. There is complex control software on the control system that needs to be tested because these systems are all safety relevant one way or another. So in case of the rail industry, we need to be careful about the passengers. In case of space, obviously there's no space for bugs and for problems which are very difficult to solve once the product is deployed. Also, wherever there are some normative requirements, there are standards which impose detailed testing, detailed validation, verification of the software, where the hardware availability may be an issue. Again, that's the scenario we're talking about with the software in the loop version, where there is no hardware to test, but we already want to test. We want to be quicker than the hardware lead times. Also, wherever the project time is a cost factor essentially. So if we just want to be sure that we'll be, or not maybe sure, but at least increase the probability of making the thing on time, and also the reachability of what we're building is limited to an extent. So in case of the rail industry, as I've already taken this example, the problem with reachability of trains is that once they get to a lot of problems with costs, problem with schedules, with times, with penalties, and it's best if the trains spend as little time in the depots as much as possible. And so we cannot afford just taking them out of the operation and then performing some fixes and tests and experiments. And we have to maintain a digital twin of this device. And I believe this is a very similar scenario in case of whatever we launch into space. Basically, there is no way of taking it back for the most part. We cannot just simply disassemble it and fix something. All we can do is try to work on the replica, on the digital twin on the ground, and try our best to fix if there are any issues. Okay, so that's about it. Now it's the time for Q&A. If there are any questions that I could try to answer, then be happy to do so.
Okay, thanks very much, Piotr. How about those questions from the audience? Go ahead. You have a chance to ask the expert. Okay, Romek?
Okay, so I have a following question, because we were have a try to make this kind of system some time ago for AOCS of one satellite. But actually, we have developed the unit which was very similar to what you are proposing. So I have faced many problems which you are facing, I suppose. One of them, which I'm wondering in the context of what you have said in the presentation, is adjustment of the whole system to the new task. I mean that it sounds, of course, great that there is a versatile system which can be adopted for some purpose to be the simulation compartment to the project. In our case, we have interfaces which were able to be occupied by physical units, or we have software emulators for those. So, for example, there was a computer which was a controller for AOCS, and there was a number of sensors and a number of actuators. And we could work with this. Of course, when it is on the table in the laboratory, you cannot verify if your, for example, AOCS algorithm works correctly. So what we did was to implement in this PC computer where the simulation of the space environment was ongoing. So we could cheat, let's say, the computer that it is equipped with all equipments, but in fact we have only a few on the table. So what is missing was supplied by the simulation. Or we could do it opposite way. So we could start to run some control algorithm on the computer and provide the data from real system or from emulators. Nevertheless, there is a certain number of interfaces which you need to prepare for this emulator box and make this whole thing running. So I think that the preparation of reliable simulation in this system is a huge effort, and especially in so when you have presented one of the first slides in the beginning, there was problems which is facing. So I would say that the time for tuning of the whole system and preparation of hardware is a key factor here, and I wonder how do you deal with this?
Okay, very good question. Thank you. So basically, we're again as a company we have grown on the railway market. Let's put it this way. So we have been fine-tuning our approach for, say, over 15 years to this, and now in many cases these projects share some common, let's say, at least interface or a concept or a common controller platform. But when we're talking about the simulations themselves, what we are doing typically is we are reaching out to our customers for any kind of documentation that we can get our hands on, and then create partially automatically, I should say. I'll talk a bit about it later, but parts of those simulations need to be created manually because those systems behave differently in different projects, right? So even though the general concept could be the same, then there are different vendors, different solutions on a given project. And so we create a specification of what is going to be simulated and then implement a specification shortly after, so that we have all the time we have the communication between us and the vendors of those subsystems ongoing, which is actually helping not only us but also them, because they have their control system and they want to make sure that it's operating properly, like in your case, operating properly with all the peripherals around it. And then people who are responsible for, companies responsible for delivering those peripherals also need to adjust to the interfaces, right? So they need to provide something that behaves as it was specified. So basing on what was specified, we were able to fairly quickly develop this behavioral simulation that I talked about. But the simulation is, let me say this again, is as complex as it needs to be, but not more complex than this. So when we're talking about logic, then we're just talking about binary logic. We're not really paying attention to the exact voltage on the wire, if it's fluctuating from, let's say, from the desired value or whatever. We're just simulating logic, whether it's 0 or 1. And this is the part of one part of the story. Another part is that we have automized as much as we could in this whole process. And one of the results of this is this thing called Elmo that I mentioned before. The Elmo is capable of taking the wiring diagrams of the system. It has a pre-modeled set of components. So all those primitive components that we would normally have to model by hand, or we'd have to get them or put them in bigger groups and create more complex models out of them. Elmo is capable of generating this model on the fly together with those basic components. And yeah, this allows us to create or to get a consistent result in the end. And we've been fine-tuning this for years and years now. And I think it works pretty well. And in case of rail industry projects, which are typically, we're talking about years here. So a project like that would be set up for 2 to 3 years. We can easily make it on time or even before time, before anything substantial is actually present in the project itself. We can already be almost ready with our simulations. That's the approach that we have. I don't know if that answers your question.
If I may, I would add one more sentence here, or a few sentences.
Sure, yes, go ahead.
Because I had a feeling that the question was more related to hardware and software integration and how we are dealing with that. And here, right? Was that your intention?
Yes.
Okay. So from this perspective, I mean, what Piotr said was more related to, because maybe from the beginning. The simulation is often based on the interfaces that are quite common and popular. And as long as there are some popular communication buses or protocols, then it's not that difficult, because that can be migrated from one project to another. And this is kind of a standard. You can buy a commercial off-the-shelf hardware modules that will allow you to communicate with the devices. And on the other hand, we are NI, so former National Instruments partner for, like it said, I think it's now more than 15 years. So whenever we can, we are using their hardware also to measure, to set the signals, and to provide the proper signals for the ECU. And also we are leveraging the possibilities that NI gives us with the FPGA that comes often with the certain signal generators or signal measurement modules. So we are able, for example, to create a very, maybe not often quite simple FPGA code that will generate the signal that is required without really designing a sophisticated board, just by connecting the commercial off-the-shelf modules with the FPGA code we are building. So, and that gives us a very big flexibility. So even if the signal has to, I don't know, change very quickly, or create some kind of a waveform that we will not be able to achieve with the millisecond accuracy simulation, we can just create the parameters of this waveform in the simulation and then provide that for the FPGA and generate the signal on the FPGA. So that's the second, let's say, approach we are using that gives us also quite big flexibility. and helps us to provide the simulation at the very early stage of the project.
Okay, I understand. Yeah, you're right that actually most systems have some standard interfaces, so most of the standard interfaces can be handled the same way or quite similar way, and problem is only with the control signals or some custom required signals, which can be at the beginning somehow simulated with the FPGA or some other features. Okay. I have another question. What is the difference between your system and DSpace, for example?
Well, yeah, there are many similarities. So kudos for pointing this out. We are perhaps a little bit too humble to consider them a direct competitor because they're a big player. But what this space is providing, among other things, comparing to what we are providing in this kind of cases, is that they have their own custom hardware platform, if you will. So you can buy a DSpace piece of equipment. They manufacture them in series. Our solutions are more tailored to a particular customer, to a particular industry. Their solutions are more generic. Also, their simulations tend to be more sophisticated in a way, meaning that they can be usually more complex, I would say. But for our use cases, we consider them to be, in many cases, just too complex. And so it's all in the balance between what we actually need in the project and what we can afford within the budget, what we can deliver within the time that we have. And yeah, they're just like a big competitor or a big company, which we're looking up to in a way, but also we're focusing on our niche, which is the fact that not only we're making a very custom-made solutions or tailored solutions for particular customers, but also we integrate them at the same time with their lifecycle management tools, which is what DSpace isn't so keen on doing, let's say. So they would gladly sell a piece of equipment for quite a lot of money, but then yeah, we are providing like the complete package.
Okay. Okay, thank you.
Yeah. Thank you.
Anyone else? So let me sum this up. Thanks very, very much, Piotr, for a very interesting talk. And I think this is the future trend that everyone will follow. We are definitely very much interested in working with you on that Elmo application that resembles a bit something that we started some time ago, never finished. And that looks like a great opportunity to have something complete done in real time. Another thing that I was thinking of when looking at your presentation, that was this digital twin when the project is almost finished and it's in operation. In our case, we usually do flat sats. Flat sats are really hardware in the loop setups when you have a real duplicate of something that has flown and you can work on it. So in many cases, you could probably do what you are suggesting, just switching to a complete digital twin, which would be very handy, especially that those flat sets are usually quite complex. You cannot use them, you cannot move them. If you want to go somewhere, you simply are stuck.
Okay.
Although you cannot use them all the time, because I remember a mission called Galileo, which was it was a JPL mission. They were supposed to, and they flew actually to Jupiter, and the Galileo was equipped with a high gain antenna that got stuck. And actually that impacted the mission for some time, and the rate of data was very small. And they were actually having a detective team that was trying to figure out the problem. And physically, they needed to have a real thing. You know, digital, it would not work at all. And they finally focused on a mechanical galling problem. You know, things got welded together during transport, and you would not be able to do it in regular simulation. So there are limits to it, although I think that the trend that you are following is just the one that we will follow.
All right, thank you. Yeah, that's a very, very nice example of what could or couldn't be done with this. Just to recap on this, in our case, what comes out of what we're building, so the digital twin in the end, is also a kind of an amalgamate of both hardware and software components, right? So there are instances in which our customers need to have, let's say, physical doors, train doors, for example, and they are in the lab, they're connected to the digital twin, they are operating together with it. The only difference is that they are using just one real piece of doors, and the remaining 11 doors are simulated in that case. So we're able to do any kind of a mixture between hardware and software in that case. But thank you for this remark. So just to conclude, we're heading to Space Tech Expo this year. So should anybody of you be present, we would like to welcome you and invite you to our booth. I'm sure we can have some nice conversations and interesting discussions there.
Great. Thank you very, very much for your interesting talk, and until next time.
Thank you.
Thank you.
Thanks for having
Yeah.
me. Take care.
Bye-bye.